Hello, my name is Lee Walston. I'm an ecologist at Argonne National Laboratory, and I'll be sharing with you some of the work we've been doing for the U.S. Department of Energy to understand bird and bat occurrence at utility scale solar sites using passive acoustic monitoring approaches. Here is a general outline of my presentation today. I'll begin with a brief background on passive acoustic monitoring in general. I'll then talk about bioacoustical analysis methods with a focus on AI tools. I'll then talk about how we apply these technologies to our projects, the DOE PHASE and DOE Inspire projects. I'll then present some preliminary results and then finish with some discussion on inferences, considerations, and next steps. So this presentation contains some work we've been doing for the U.S. Department of Energy under two projects, Inspire and PHASE. Both of these projects are similar in that they both involve research on the biodiversity implications of habitat-friendly solar. There are numerous research partners in both of these studies. In total, there is biodiversity research being conducted at about 25 research sites across the country. However, Argonne has been involved in research at about 11 of these sites. So that's where I'll be focusing the bulk of my talk today. The use of passive acoustic monitoring and ecological research has been steadily increasing, in part due to the low cost of monitoring equipment and improvements in the detection and analysis tools. Real quick, before we dive into things a little bit more, I just want to explain, there are a lot of advantages to using passive acoustic monitoring tools. They are less invasive than traditional methods that involve people visiting the site. That can obviously reduce the amount of time and labor costs associated with all the field work. They provide a mechanism to store data that can be reanalyzed at a later date. You can collect a lot of data that can be used to answer a lot of different types of questions. And you can also use acoustic data to possibly detect species that could be missed by other traditional methods. However, all of these advantages also produce one main challenge, and that is figuring out how to handle all the data, because these methods do produce lots and lots of data that need to be analyzed. So the key question is, how can we best process the data from these recorders to extract the most meaningful and defensible information that can support decision-making? This is one area where we believe artificial intelligence can really help. A lot of research and development has produced AI-enabled tools to expedite bioacoustic analysis. I'll cover two of them in this talk. One of them is called BirdNet, obviously for birds. It's a relatively new automatic species classifier that uses deep learning to identify over 6,000 species in its current development state, over 6,000 species worldwide, and it's developed by the Cornell Ornithology Laboratory. The second software, it's a commercial software. It's called Kaleidoscope Pro. It's a commercial software that conducts automatic bat identification based on the bat's ultrasonic recording. And it is developed by the company Wildlife Acoustics. Okay. So these are two I'm going to cover in this talk. There are more ways to analyze bioacoustic data, but these are the two I'm going to cover today. I'm going to spend a couple of slides talking specifically about BirdNet, since it's fairly new and hasn't really had much research application yet compared to the use of the BAT automatic classifiers such as Kaleidoscope, which have been more widely used and vetted in the research community. For BirdNet specifically, first, a user would obviously collect a bunch of acoustic files from their study sites. They would then use BirdNet and import all of these acoustic files into BirdNet along with information about the site's location. So the lat-long coordinates for the recorder and the time of year or the weeks in which the recorder was collecting the data. BirdNet then scans the spectrograms of each recording and uses the locational information and that temporal information provided by the user to create a species list from the eBird checklist. So BirdNet then uses deep learning to, along with that eBird checklist, to make species predictions based on the species that are likely to be present in that location and at that time of year. The standard BirdNet output are tables like these down here at the bottom that identify bird species every 3 seconds if a bird is actually detected every 3 seconds, BirdNet provides a confidence score for each detection with a default range of between 0.1 and 1, or 10% and 100% confidence, with a confidence score of 1 or 100% being very high confidence that eBird believes, not eBird, I'm sorry, BirdNet believes that species is correctly identified, and a confidence score closer to 0.1 or 10% indicates low confidence. So that's the default range, 0.1 and 1. Here's an example output table, which lists the acoustic file, the start and end times. Note that the start and end times are separated by 3 seconds, and the species detection and the confidence level. A user could use this table to manually screen, review, and listen to segments of the call at these precise sections to confirm the BirdNet detections. For example, we've got barn swallow here in this recording, and BirdNet says that this is about 99 or 100% confident that it's a barn swallow. We can listen to the recording. I don't know if you picked that up or not over the audio, but that is barn swallow. The second one here is an American goldfinch. And again, we can listen to this specific recording for American goldfinch. So that's American goldfinch. That's that specific spectrogram corresponding to this time segment within the recording for the American goldfinch, which was correctly confirmed. And then finally, we've got looks like a prediction for American robin down here. Again, pretty close to 100%. We can listen to that here. So yeah, that sounds like American robin. Yep. And so, a user could, identify the start and the end times within the recording, and then go in and generate spectrograms to confirm each species. And in this case, all 3 of these species were confirmed. These were pretty easy ones, right? So while a user could follow that process to manually confirm and verify species that are predicted by BirdNet, one of the main questions is how can we use BirdNet? How reliable is this automatic classifier, or any automatic classifier for that matter? And how can we best understand the results and determine how precise and how useful this classifier is? One of the main considerations is that these automatic classifiers generate millions of detections. We've generated millions of detections with the deployment of our acoustic recorders at solar sites, making it nearly impossible to go in and manually confirm each one. Instead, we need to develop approaches to assist in confirming species detections and the assessment of classifier performance, like understanding false positives, false negatives, how accurate is it, and developing a way to understand the classifier performance is really useful in this case to inform how these approaches can be best used for research applications, and to inform which are the best metrics to use. So tools to validate bat classifiers have been developed and are more widely used. They're often embedded in the commercial software or the other tools to automatically identify bats, such as the Kaleidoscope Pro software. But what about for birds? There are usually fewer than 12 bat species in a given area, but there could be a lot more birds. There could be over 100 birds in a given area, making it more difficult to really evaluate the performance of any classifier for birds. So there are a lot of the literature currently focuses on methods to evaluate BirdNet performance and the performance of other automatic classifiers for birds. And most of these recent studies have found that BirdNet does perform pretty well compared to manual annotation of acoustic recordings and other conventional methods like point count surveys. But a key consideration is determine what is the key confidence threshold to use. And there's a trade-off here, because using a high confidence threshold could increase the number of false negative detections, but using a lower confidence threshold could increase the number of false positive detections. And so what we did in our work to start is we identified 30 focal species, and then we manually reviewed 60 randomly selected BirdNet detections for those 30 focal species, and using a confidence threshold of 0.25. So we filtered all of our bird net detections to a minimum confidence threshold of 0.25 or 25%. And we found that BirdNet got the majority of these predictions right at a confidence level of 0.25. Precision was greater than 75% for the majority of these focal species, all except for 4, which you can see over on the far right-hand side of the graph. As noted by this red line represents that 75% precision threshold. And so going forward here, at least for the preliminary purposes of this presentation, we presume that since confidence at 25%, so a 25% confidence level for BirdNet, since that performed pretty well, then it stands to reason that confidence level at 50% would be just as good, if not better, in terms of precision. So for a starting point for this analysis and all the discussion going forward today, for BirdNet, we are using a confidence threshold of 50%, 50% confidence threshold. So before getting into results, we need to talk about our study design and the key questions that our team has been trying to answer with these passive acoustic monitors. Our overarching research goal is to understand the patterns of bird and bat occurrence at solar sites, and we aim to accomplish this through comparisons of bird and bat activity, species richness, and species diversity on the solar sites compared to these metrics in offsite reference areas that represent the pre-solar land use. Oftentimes this is agriculture, right? All of the 11 sites in our research were previously row crop agriculture, as shown in this example map here. The red polygon shows the subject area before solar development. So this was an agricultural field before solar development, and now it is a solar site. It's been converted to a solar site. And this land use conversion is typical of most solar developments that we see in the Midwest, and it's true for all of the study sites in our projects. All of our study sites were also planted with vegetation and managed in a way to provide habitat for pollinators and other wildlife. Although the seed mixes and the precise management styles, they tended to vary a little bit site by site. All of them were planted with some form of solar pollinator habitat. And based on the previous land use, we hypothesized, since previous land use was row crop agriculture, we hypothesized that the establishment of solar habitat in these sites could result in observable positive responses in the bird and bat communities. So possibly increased activity, increased species richness, increased species diversity. We therefore developed a study design that involves passive acoustic monitoring on these sites and in these offsite reference areas to make these comparisons. In these offsite reference areas, we predominantly used row crop agriculture, so corn, soybean fields. This involves setting up acoustic recorders on the solar sites at least 100 meters away from the edge of the solar facility, and also in offsite reference areas. These are the edges of row crop agricultural fields. So we place these recorders on the edges of agricultural fields, oftentimes along fence rows or grassy waterways that separate agricultural fields, those kinds of things. We don't really know the detectable range of these recorders. It depends on factors such as how loud the birds are, presence of background noise, the presence of noise barriers, but we're currently assuming 100 meters as our general rule of thumb when we're setting up these recorders, trying to get them at least 100 meters away from anything else that could possibly influence the study design. So on the solar sites, we want these recorders at least 100 meters away from the edge of the solar site, so to speak. We've been recording at some sites since 2021, and we've expanded to more sites and reference areas by this year in 2023. The results I'm about to present are for this year only. While year-round monitoring is conducted on some solar sites, comparisons to off-site reference areas is restricted to much more narrower windows of time, the spring and the summer months, when we have permission to set up the recorder so as not to interfere with farming activities. Before we look at some preliminary results, I just want to note that all of these sites have been anonymized, and I'm only sharing results from a few sites, not all 11 sites. We're still processing the data. Let's first look at birds using the BirdNet classifier. When we calculate avian activity, which is calculated as the total daily number of bird detections that, again, meet that confidence threshold of 0.5. We summarize those results across week. So what we're seeing on these graphs represent the average daily activity by week. We see mixed results. This is just looking at 4 sites. We see pretty mixed results. At a couple sites, we see that off-site activity, off-site is denoted by the brownish, yellowish line. On-site activity is denoted by the green line. In all cases, on-site is green, off-site is brown. We see mixed levels of activity. At 2 sites, activity is higher off-site, and then at the other 2 sites, activity is higher on-site. And again, you can kind of note the differences in weeks down below. The graphs have different temporal ranges along that x-axis that might vary from site to site. We have at least, however, 1 month of data at every site. So you'll see at least 4 weeks presented along every x-axis. Here's another way of looking at avian activity, where you can kind of see the distribution of species that are detected, again, at or above that 50% confidence threshold. These are stacked bar charts. These are stacked bar charts of the total BirdNet detections each week. For each week, the top graph represents on-site activity and the bottom graph represents off-site activity. At those first 2 sites where off-site activity was greater than on-site, we see that most of the activity was just driven by 2 dominant species, horned larks and indigo buntings. On-site, we see much more diversity, albeit at lower overall numbers. At the bottom 2 sites, we see that total detections are higher on-site, but the difference in species composition aren't observable in these graphs. It's not until we see some of these other graphs that we start to see some patterns emerge, at least for these 4 sites. So based on the previous bar charts, you might get an idea of species richness at all these locations. Here we are looking at graph species richness at each site measured as the daily total number of unique species detections. Again, at confidence greater than 50%. Summarized across week again, we see that avian species richness is consistently greater on these 4 sites than in the off-site reference areas. At some sites, there are more than 10 additional species detected daily on the solar sites than in the off-site reference areas. What about avian species diversity? Well, we calculated that in the same way by calculating the Shannon Diversity Index for all daily BirdNet detections. Again, summarizing these daily metrics across weeks. We summarized and graphed them over the monitoring weeks, and we see a pretty consistent pattern across the 4 sites again, and that is that there's greater species diversity on the solar sites than in the off-site reference areas. There are a couple of moments, however, in site number 4 where species diversity might be a little indistinguishable, but overall, the pattern overall is pretty clear, at least for these 4 sites, greater species diversity on-site than in these off-site reference areas. Now, what about bats? We processed all of our evening ultrasonic recordings through the Kaleidoscope software to determine which files are most likely to contain bats and which are noise files, and to also determine nightly patterns of bat activity and species richness. I should mention our recorders first. Our recorders that we're using are Wildlife Acoustic Song Meter Bat Mini recorders, and they are recorders that allow us to not only record bat ultrasonic acoustical frequencies at night, but also to record bird calls during the day. So it's one unit that has an acoustic microphone and an ultrasonic microphone attached to it as well. We program the recorders to record birds 4 hours a day, so 2 hours at sunrise and 2 hours at sunset. And they're also programmed to record bats for 3 hours each evening from 9 p.m. to midnight each evening. So a lot of data each day coming in over the peak monitoring period from about March to September. I would say that's where most of our overlapping data sets between on-site and off-site activity are located, from March to September. So back to bats. We only have results so far for 2 sites. As you can see in these graphs, analyses are ongoing. Beginning with bat activity, again, calculated in the same way as bird activity, total daily number of bat detections. We see that things are pretty mixed, right? At one site, we don't really have any distinguishable pattern of bat activity. At the other site, we kind of do. We see that bat activity on site is consistently higher than bat activity off site. Okay. Looking at the stacked bar charts again of bat activity, we see that there are 5 species detected at these 2 solar sites and in the reference areas, with by far the most frequently detected species being the silver-haired bat. It was detected at every location, and we're currently in the process of going through and manually confirming through Kaleidoscope all of these bat species detections, and so that involves using the manual confirmation methods embedded within the Kaleidoscope Pro software. But right now, I should say right now, all of everything that we're sharing here are generated from the automatic ID feature of Kaleidoscope software. And if we were to look forward at bat diversity and species richness, I'm not showing species richness here because it's almost a mirror of diversity. We aren't seeing very noticeable patterns in bat species richness or diversity at these 2 sites, possibly because we have such few bat species, just a total of 5, and then all 5 of them were detected at both sites and in their off-site reference areas, albeit some of them might have been at different times of the week or different days of the week. And so you can see here they're mixed, indistinguishable patterns of bat species diversity. So what can we start to gather, at least initially, from this kind of approach? Well, for one, we see that activity is mixed for both birds and bats. At some sites, activity is greater on-site. At other sites, activity might be greater off-site, or there might not be any distinguishable difference, at least graphically speaking, between sites. I'll also note that we have not run any statistical analyses on these yet. We're just looking at graphs. The results that we're at least preliminarily seeing for activity are sort of an interesting contrast to some of the recent research that's been emerging on bat activity, at least for bats in the UK. The recent study in the UK found that bat activity was lower on the solar sites compared to offsite reference areas. Our very preliminary results from just 2 sites don't really support this, but being from only 2 sites, it's still too early to tell if that trend is going to be upheld or if that's really a meaningful finding. We also noticed that patterns of species richness and diversity were different for birds and bats. We consistently observed greater avian species richness and diversity on our solar sites, but these patterns weren't very observable or distinguishable for the bats. Again, we'll look to see if these patterns are upheld across all of our other sites as we continue our analyses. And finally, we need to bring into this whole discussion and this whole analysis some of these other landscape factors that could influence everything that we've been talking about, right? And these are factors that could influence the presence of and the detectability of birds and bats in the vicinity of the recorders. And it should be accounted for, as whether it's covariates or other random factors and analysis that we can add. And these factors include, such things as the percentage of trees and forested areas within a certain distance from each of our recorders, distance to water, and the proportion or the amount of certain sound barriers that can influence how sound travels across the landscape or within the solar sites. And I want to talk about that factor specifically because it could be particularly influential in these research designs at solar sites. And that is the question of whether or not solar panels can influence detectability. It's known that solar panels can act as noise barriers. Studies have suggested placing them along highways, for example, to block traffic noise in nearby residential areas, right? And so is it possible that they can act in a similar manner to block natural sounds and soundscapes such as avian and bat vocalizations from longer distances? And if that's the case, if so, is it possible that these off-site recorders placed in more open landscapes could have a larger detectable range than on-site recorders? Okay, so that concludes my talk today on bird and bat monitoring methods at solar sites. We continue to collect data and analyze data, and hopefully within the next year or so, we'll have much more information and a much better understanding of patterns of bird and bat occurrence at solar sites through the use of these monitoring methods and analytical approaches. Thank you all very much.